Hang on. Okay, it's okay. Just let it go.
4 seconds, 5 seconds.
It's fine. Is it running?
Yeah,
Okay, good.
running for 5 seconds.
Okay, good. Let's go. Now, what's the implication? So let's take a look at two sources coming in. So when you got a light source from the far away star, it comes in and it spreads. That's the problem. Yeah, it spreads. So by right, a star, a bright spot should cause a spot. But it doesn't cause just a spot. Because of the physics, it spreads. Right? We just learned that it spreads. So it causes this pattern over here. Now another star, let's call this star B. Now star B is far away, so what happened is that star B will form its own patch. So this is B, this is A. So no problem. The two patches seen as two patches. Two dots seen as two dots. That's good. Yeah? And it's really bad if you got actually a binary star and you thought that you see it as only one star. That's bad because you cannot see the resolution. You cannot understand what's happening inside the binary system. So what happened is that if you've got two stars getting rather close to the point where A and B are separated so that, can you see that the first minima of B is right overlapping with the maxima of A? Now when this happens, the resultant intensity is going to look like this, something like this. Something like this. So what happened is that if you look at this intensity pattern, you're just going to see a bright patch over here. You're not going to see two bright spots like this and like this. So what happened is that the two light patches from the two stars merge into one. Do you want that to happen? No, you don't want that to happen. You want to see two dots. Imagine you point the satellite, the spy satellite into the, say, some enemy base. So the enemy base is supposed to have like the tanks. You want to see 8 tanks, right? Then suddenly you just see one big blob of like, what the what earth is this? It's like one big amoeba kind of thing. Yeah, which is bad. I mean, you want to see 8 tanks, yeah, 8 missiles, not one big blob over there. So that's useless. You want to see the resolution. Yeah. So this is the limit to what you can, when you cannot resolve anymore, when you can just resolve. Resolve simply is a complicated word for being able to see two separate things as two separate things. Yeah, so this is what we call two objects resolve. This case is when it is just resolved. Cool? Before we go into the technicalities, right, do you think it is good for the spread to be as small as possible or as big as possible? Yeah, the spread, this spread over here. If it is big, do you agree that the overlap will happen very soon when the theta is still very big? When the spread is small, it means that I can pack the two sources really close together before this happens. So it's good for the theta to be as small, the spread over here to be as small as possible. That's why, remember theta equals to lambda upon d. This theta is the spread, the half angular spread. Just now we went through just now. So that's why telescope, they want this to be as big as possible, so that the theta is small. So it serves two functions. Yeah? The reason why good telescopes have big lenses, and the reason why it's expensive, I explain later, is that they have big aperture. Now big aperture means that you can resolve very well. Two stars can come really close before they can no longer be seen as two separate objects. And also the bigger the lens, the more light you capture. Yeah? And it's important for you to be able to resolve, because if the telescope cannot resolve, no matter how you magnify digitally, it'll still be just one big blob. Just one blob, and biggest blob. Useless, right? It's when it is resolved, that's when you magnify, that's when they get further and further apart. Agree? Okay? So it's very important for you to resolve. So, coming back to this, what's this condition called when it's just resolved? It's called Rayleigh's criterion. And you need to know how to state this, okay? Rayleigh's criterion. It's in your notes, so look up for this thing called Rayleigh's criterion. Can you find it and then put a lot of stars around it? Because you can be asked in exams, state Rayleigh's criterion. So put a note there, must know how to state. It states that when two objects are just resolved, make sure you highlight the word just as well, because if in the exams you say resolve or not resolve, I am going to mark you wrong. Make sure that you say just resolve when the first minima of one source overlaps with the the central maxima of the other source. Cool? Rayleigh's criterion. Okay. Now, there's something I'm going to go through here which is really important and you need to pay close attention. What's the distance, if I call this angle theta over here and this is 0 angle, what's this angle over here? It is the angle between the central maxima of A and the first minima of A. Isn't theta equals to lambda upon T? We learned it just now. Right? We learned lambda equals to theta equals to lambda upon D, which is the angle between the central maxima of A and the first minima of A. Now, do you agree that by Rayleigh's criterion, that's where the maxima of B is? Right? That's where maxima B is. So therefore, the separation between the two maximas is equals to this. Which means the separation between the angular separation between the sources must also be this. Now, hang on. If I call this X and this as L, can you see that this is also equals to X upon L? Yeah, the circular measure thing. Yep. Because this is the separation between the central maxima and the first minima, which is also equals to the angular separation between the sources. So when this condition is met, then you have Rayleigh's criterion, two objects are just resolved. Let us try it on an example so that you can appreciate, first of all, how to apply the equation. Second of all, how good our eye is in resolving things. Now let's take a look. Imagine that you, on a day where you're very bored, you start looking at the headlamps of cars. So, I'm going to ask you a few questions on estimation. First of all, estimate the size of the pupil in your eye. The pupil, even though you don't take bio, let's understand our eye structure. The pupil is not the dark portion of the eye, it's a darker portion of the dark portion. Yeah.
So, but the size of the pupil is according to your eye.
Approximate, that's why I asked approximate. No matter how you enlarge your eyes, you don't enlarge the pupil unless you switch off the lights. 2 mm. Okay. Estimate the size, the distance of separation between the estimate the separation between the two headlamps of the car. Car. Say BMW 5 Series. 5 centimeters. Even Mini Cooper not so small. BMW 5 Series, not BMW 5 centimeters.
I think it's a toy series.
Those kind you pull backwards and let go kind of.
Also, it's on the two sides of the car.
Yes, two sides of the car.
You draw vertically.
Roughly how far are they apart?
2 meters.
2 meters. This is about 1 meter. 2 meters? Lorry lorry 1.5 Yeah? Yeah, okay. So my task for you is to find the L before the two headlamps can no longer be resolved as two headlamps. That means the car is so far away that the two headlamps, one blob of light. Okay, assuming that lambda is 600 nanometers. Go ahead, find the L. So your task is to find L so that the two headlamps can no longer be resolved as two headlamps. It becomes only one headlamp. The same thing goes. How far is the person away from you before the two eyes can no longer be seen as two eyes? That's quite creepy, but that's quite creepy. That's quite creepy. Go. Give it a try.
5,000.
Yeah, about a few kilometers away. Yes, correct. You'll find that it's a few kilometers away before they cannot be resolved anymore. But obviously in real life it's going to happen earlier. Why? Because so many of you spend so much time on handphones that you become myopic. You got, what do you call this? Astigmatism. You got astigmatic. Yep. And then when 5 kilometers is far enough for atmospheric distortion to come in as well. Yeah, atmospheric distortion will come in as well. You know how far is 5 km from here? Or? From here to Vivo City is about 9. So it's half the distance from here to Vivo City. It's actually very far. Yep. Our eye is sensitive enough to see a candlelight about 10 kilometers away. in a complete darkness.
Where
In
is
complete
it?
darkness.
Complete darkness.
Complete darkness, yes, correct. 10 kilometers away.
Yeah.
But hang on, the stars are very bright, by
Stars
the
are
way. Yeah,
very
actually,
big,
the stars are very the stars are not candles. Someone put a candle up there.
So 5,000.
Yeah, yeah, correct. Yeah, 5 kilometers away. Can? So with this, we're going to try some other examples tomorrow on resolution, and then we're going to do other things. Can? Tomorrow we got a lesson at 2 p.m. I think, or 2:20. Can you press the stop button? Thank you. Huh?
It's still recording.
Okay.